Okay, well, welcome back. Now we want to create the CU. We call it CU and DU integration, or the connection between the both circuit. Or uh, okay, this one. All right, or we can just draw like this. Yeah, we can have this, which is our DU, and we have our CU. Okay, this is our CU, this is our DU, and the control signal will be connected, or will be the output from the CU to the DU, which is this. The signal is we have the LD1, LD2, we have SEL, we have OP, we have EN, right? And here the DU, we have actually the data out, and we have input also, which is data in, and also we have the rack 1 and rack 2, the one that we create to see the content of rack 1 and rack 2, and and of course we have the clock and reset. And for the CU, we have the start input, and of course we have the clock, and this is a negative H, and we have the reset also, and we have one output here. Yeah, we want to see the state, right, which is 3-bit, and this is 4-bit, this is 4-bit, this is 4-bit, and this is 4-bit, right? So this is the circuit that we want to create. Yeah, so we can have this here, and create a new project. We have a new one. Save this first, and is it okay? Oh, why? Oh, we have this thing. No. Okay, so we create a new project, and remember we need to have a new folder for this one. Let's name it this. And this now we because we will have these two, our previous design, CU and DU, so we need to add this design to our new design, which is the first one is DU, CU, the second one is the DU, right? Just add this, and we can finish here. Okay, so module, the name is this, and we need to list all of the input and output here. So you can start with clock, reset, start. Okay, we have state, we have data in, we have data out, we have rec 1 and rec 2. Okay, that's it. So our input will be clock start is the 1-bit input. What about others? Data in is 4-bit. And for input, we have output, and the size is 4-bit. All right. Data out, we have rec 1, we have rec 2. All right. And we have this all, which is the wire in this case, and all are 1-bit. All right, so that's it. Any other signal that we missed? No. Now we want to instantiate the CU, so we can actually go to this and open the CU. So this is our CU, and of course the name is this. We can copy all this actually, put here, and the name now is CU, CU here. All right, so just like this, the name is CU, or can be other name, and the port arrangement is just exactly based on this, and the name is the same here. But if you use the name, different name, for example, this one you use clock, so here you need to have clock, yeah. So must be the same as this one, but as because we use the same name, so this is easier, so that we can use this, yeah. And we have the DU also, which is this one, and we can actually use all of this. Just give it a name as DU here, and this is the same. All right, so and it should be done for this. All right, so done. Save this design to the folder. Use this, and we can okay, there is error. State is not declared. Okay, so this is syntax error, module declaration error. So we can here state is, yes, we forgot the state, yeah, right? The output state is 3-bit. Yeah, we have another one, state. All right, so we forgot this. State is not declared as a port. Yeah, we have in the list, but we don't have declared this whether it is input or output. Okay, and we run again. All right, and 6 warning is because the warning in the data path unit, and we know this already, and this is no problem for us, right? So it should be uh, no problem, should be okay. So we proceed to the Testbench. All right, so we write the Testbench for this. Okay, in the Testbench we can have this time scale. We use 1 nanosecond, 1 nanosecond time unit, and 1 nanosecond precision. All right, and module, we just name it as CU DU Testbench. All right, and we want to do this, right? So we can actually copy this to this and make sure that we change this to right. Yeah, in Testbench, input is declared as right and output declared as wire. Okay. And now we instantiate our design, the design that we want to test. So the name should be this one. All right, and we name it as DUT, design under test. And because we use the same name here, and so we can actually use this. All right, straight away use this. Should be done for module instantiation. And now we want to create the we want to monitor the signal. Right, so we can have this command. We want to monitor the time versus the time, and we want to monitor this all. Right, and this should be in binary, and all are in binary. And we want to map to this. Done for this, and maybe here we where is the cursor? We have clock to 0. We start clock with 0. If we write 1, we will start with 1. Right, and we can create the clock. Right, if we write like this, means that we want to toggle the clock every 10 nanosecond. Means that the period is 20 nanosecond. Yeah. Okay. And we want to give the stimulus to our design. At time 0, what do? Maybe we reset our circuit first, right? And the start is equal to 0, and the data in, make it 0 first. All right, and after that, after maybe 25 or 30 nanosecond, make reset equal to 0, 0. All right, and another 10 nanosecond or 5 nanosecond or 10, depend on you. We make the data available. Data, for example, 2, data in equal to 2. This is for X. So next, another 20 nanosecond, we force the data in to be 3. Right, but before that, let's have a start signal here. Start equal to 1. All right, and here we stop the start signal. Okay, and we will simulate this until how long is it? Another 100 nano, and we stop. Okay, so this is our stimulus. So you can have many more input here, but this one we want to test the first time test. Maybe we have this first, and let's see what happened. Okay, so and we need to save this, save this name. Okay, and we try to look for any error. No error means that the code is correct. Right, and the warning, we know this already, so should be no problem. Now try to run. But before that, we need to do this setting. Okay, this is the name and the file. This one. Add. Okay, and click OK. And we run the RTL simulation and wait for the waveform. Okay. All right, so this is the waveform. Is it correct? So maybe we change this to unsigned. All right. Is it correct? So we have the start here, means that we go from this state 0, state 1, state 2, state 3, state 4. We have read data out. We don't want to look at data out yet, so make it here. Data in is 2. Oh, this is too short for data in, so 2 is never go to 2 never go to rack 1, yeah, the X. So we need to change because we have 2 short. Yeah, we read here at state 1 we should read x, and here we change the y already. Y is 3, so we should have x until here, all right, or until here, right, at another 20 nanosecond, right? So we change this to a new one. Okay, this is start. So maybe we have this, and start equal to 0. Yeah, all right, we disable the start. All right, make it longer for data in so that we can see. Okay, so again we change this to unsigned, and the out we put at the last one. We start here. This is the start signal. All right, start, and we have number 2 for x and number 3 for y. So x is 2, and at state 1, this is state 1, right? State 1 we transfer x or 2 into rack 1 here, and at state 2 we transfer x into rack 2 here. This is rack 2, so x is in rack 2 already here, and next we transfer y, this is y, into rack 1, and the last state we add, yeah, we add x and y, which is 2 plus 3, we have number 5 in rack 1, yeah, rack 1. So this is the result, this is 5, right? So this is how this thing work, huh? So means that our design is correct, and we can have many more simulation, yeah, simulation input. So for example, in our when you look at the nodes here, so this we have two operation. So we have x equal to 2 and y equal to 5, yeah, x equal to 2, y equal to 5. So we can see that here x in state this state 1, so x is now in rack 1, and state 2 x is now in rack 2, all right, and for state 3 we have y5 here, and state 4 5 plus 2, all right, we have 7, right, and we change x to 4 and y to 6 in the next operation, so we can have the output is a, yeah, 4 plus 6 is a, yeah, in hexadecimal, right, at the state number 4. All right, so in this case we have 2x and 2y, yeah, and if we have another one, we can check for other number as well, right? The only thing I want to explain to you in this slide is that this the CU, yeah, the design of the CU is a little bit different from what we have here in these quarters. The CU, yeah, the CU, this. So here we have a separate signal here, LD1 equal to 1, LD2 equal to 0, and so on and so forth. But here, this one is group together in the name of CV here, right? Group together in the name of CV, all right? And this is 5 bit, and CV is actually bit number 0, CV0 is EN, CV1 is OP, all right? So that inside here we can write something like that, this, yeah? Okay, so CV is, for example, S1, yeah, CV is 14. So what is 14? 14 in, if you look at this the CV. So what is 14? And it is declared as H, yeah, 5 bit H. So 14 in hexadecimal 4 is 0100, and 1 is 1, 000, but we just declare as 5 bit, so it should be this. So this is bit number 0, number 1, number 2, number 3, number 4. So if you look at what we have here, number 4 is actually LD. CV number 4 is actually LD1. So this is LD1 equal to 1. And number 2 is SEL. SEL equal to 1. So this is exactly the same with this one. All right, as LE1 equal to 1, SEL equal to 1. Yeah, same thing actually. All right, but different style of code writing. Yeah. Okay, so any question before we go to the last part, which is the exercise here.